In this video, we're going to go over radioactive decay, which was discovered by Antoine Henri Becquerel, a French physicist, in 1896. So how did he discover it? Well, first of all, he was looking at fluorescent compounds of uranium and how they would emit X-rays when exposed to sunlight. But he placed his experiment in a drawer and was surprised to find that his experiment worked even though the material was not exposed to sunlight. From this, he figured that radiation must be coming from uranium. Then came a husband and wife team to do further explorations into radioactivity. We're very proud of Marie Curie being Canadian, but sadly she did die from radiation sickness and exposure to radiation and her work with her husband. Now here we're going to look at this graph, which is very interesting and it's kind of crucial. Right now, I mostly want you to focus on my black dotted line in the middle here. Now my y-axis is my number of neutrons and my x-axis is the number of protons. This thin black straight line is a 1-to-1 ratio when we have an equal amount of protons as neutrons. So when the number of protons equals the amount of neutrons. Now this dotted black line here is my stability line, or what we found that atoms or elements are stable at. Now if we notice, once we get super big, like past 82 protons, something happens. What happens? There's no more stability atoms or stable atoms. And then something else we know, look at the very bottom here. My ratio is 1-to-1 around. Till eventually we get over here in my bigger ratios, this is around 1.5 to 1. So we have 1.5 neutrons per every proton. Now this is kind of important. So all elements want to be in this black line, and they're going to either decay or go through a transformation to get to these black lines. And we have certain types of decays that we're going to learn about now. So everything's unstable and they want to eventually get to this black dotted line here, which for bigger elements we have more protons, we have more neutrons than protons, and for smaller elements they tend to be balanced at 1-to-1. So what kinds of radiation are there? Well, Rutherford and others identified 3 types of nuclear radiation. The first is alpha, which is essentially the emission of a helium atom from the nucleus. The second is beta, which is the emission of an electron. My third is going to be the emission of a light energy, which is a photon, and that is gamma. Now, one thing to notice here is look at right here how many nucleons there are. There's 4, so this is the atomic mass, and we're losing 2 protons. Now, let's look at an electron. We have a -1 here. That's kind of interesting because what ends up happening is if we're getting an electron, we're actually gaining a proton in the nucleus, because what's happening is an electron's leaving, causing the nucleus to gain a proton and lose a neutron. And if we remember, we saw a difference in mass between a neutron and a proton. Well, if a neutron loses an electron, that actually makes up the mass of difference between a neutron and a proton. The next one is gamma, and if we look at gamma closely, we have absolutely no masses for gamma and no charges. Now these are key things to pay attention to. So originally they classified these radiations based on what they could penetrate and how far. So alpha was only able to penetrate a few sheets of paper. Beta was able to go to 3 millimeters of aluminum. And gamma can penetrate several centimeters of lead. It also doesn't hurt to know about the positron. So a positron happens, and this is beta. This is also here beta radiation. What happens here is when we have a proton turning into a neutron, because a proton is losing its positive charge and releasing something called a positron. So now let's go back to that graph that we were looking at. And I want you to pay close attention here. So when we're looking at this graph here, remember, we have our y-axis is telling us the amount of neutrons, and my x-axis is telling us the amount of protons. Now let's look at where we get alpha radiation. Remember, that's releasing a helium atom from the nucleus. It's all with our bigger elements way over here that are unstable. Remember, they always want to try to get to this black line here. Now, let's look at where we get a positron beta radiation. So we're releasing a positron. That is all here. So remember what's happening. We went over before. What's happening when we are releasing a positron? What's happening inside the nucleus? And now for the next one, let's look at when we're releasing an electron. These are all the ones we're releasing an electron, and we're creating something else in the nucleus. Something's shifting. Now what I want you to do is pause your video, and by looking at this graph, I want you to see if you could figure out how you could determine if you're going to have maybe, if I put a point anywhere on this graph, if it's going to be maybe alpha radiation, a beta radiation of an electron, or a beta radiation of a positron. So I want you to pause the video and see if you can figure out where and why that radiation is happening. Welcome back. So now we have another concept check and something for you to pause the video and try and figure out. So this diagram here shows the paths of an alpha particle, a gamma particle, and a beta particle. Now this beta particle is going to be when it releases an electron. If it releases a positron, it's going to look like this. We're going to look something like this instead if it releases a positron. So that's if it's 0, positive 1. Now why do you think these particles move that way? So I want you to think of what we learned before about magnetic fields, charged particles moving through magnetic fields. And now look at the properties that we know of all three of these particles. Why would the alpha not bend as much as the beta? Why does the gamma go straight? Why does this beta, an electron, go up while a positron goes down? So I want you to be able to pause the video and see if you can answer these questions. So now before we get into computing decays, let's first look at two laws that we must understand. First is the conservation of a charge. The net electrical charge cannot change in the decay process, meaning my original charge, or the sum of my original charges, must equal to the sum of my final charges, or the products. The next one is we need a conservation of the atomic mass unit, which means the total number of atomic mass numbers for my original product must be the same as my final product. So the nucleus can't change. That's not to say the atomic mass can slightly change, but our mass numbers cannot change. So let's see what this means. So first one here, we have polonium-214 undergoing alpha decay. So for this, I like to write my alpha first. So we have an alpha decay, which is a helium. So right here, that means this polonium is going to lose 4 mass, so neutrons and protons altogether, and 2 protons. So altogether it's going to lose 2 protons, 2 neutrons, which is going to end up giving me now, so the plutonium is no longer going to be, or polonium is no longer going to be polonium, it's going to be instead lead. So we're going to have 210, and we're going to have 82, and this is going to be lead. We use, remember, our atomic number to figure out which element it is. And if we look here, we have the same masses. Now let's take a look at my next one. The next one is going to be thorium. So thorium is undergoing alpha decay again. So let's write my helium, or we could just write alpha. It's up to you. And we're going to add it to see what happens here. So we're going to go to 226, because this number here and this number must equal to 230. And then 2 plus something equals 90. That's going to be 88. And the 88th element is going to be radium. Now let's look at my last one. Here we have cobalt is giving off a neutron. So with this one, we're just going to have a neutron. And a neutron has 1 there and 0 charge. Or in other words, it's not losing a proton. So if we add these all up for the nucleus, I'm going to end up with 59 and 27, and it stays as cobalt. So here are a couple questions for you to pause the video and practice. These are the answers to these questions. Here's another question for you to pause the video and think about and write down why you think electrons are not considered when applying the conservation law for atomic mass number. So before we get into some energy calculations of radioactive decay, we first must go through some more definitions. So my original element is going to be my parent. And then my new element on the product side is going to be my daughter. The daughter is what's created, the parent's the original. So let's look at an example here from before. When we looked at polonium-84 and it underwent alpha decay, well, what is my parent and what is my daughter? Well, the polonium-214 is going to be my parent. And my daughter is going to be the lead-82, or lead-210.